Assalamu alaikum. I hope all of you will be quite fine. Our today's article is article 2.6 free vibrations with viscous damping. So in the start of this chapter we have covered free undamped oscillations before midterm exams, and after midterm exams we are first starting this lecture article 2.6 free vibration with viscous damping. So as we are familiar that what is damping is actually a way of controlling the oscillations or vibrations. Their intensity is controlled by the damping. So there are types of damping as we have already studied. So viscous damping is where a viscous fluid is actually used. So free vibrations with viscous damping. So similarly, as we had derived the relations for the undamped free oscillations, we will again be deriving the governing equation using Newton's second law. First of all, it states that equation 2.58 that F is equal to minus Cx dot. So what is F? F is actually the damping force. So here you can see the schematic diagram here in figure 2.21, and this is the schematic or model diagram. And here as you can observe that mass which is actually a point mass is connected by a spring of constant or stiffness K and damping constant. Remember this letter C is in small, like this K. Small letter C is used for damping constant. So here a damper is used like a piston cylinder system where both are relatively moving with each other, and this is the mean position and equilibrium position O, and the response is actually assumed to be taken positive while the mass is moving downwards. So this is quite arbitrary, that as the system is in the vertical orientation, we can either take the reference direction of x-axis to be positive upwards or downwards. For the purpose of derivation in this textbook, the author has taken the x to be positive downwards. So here is the FBD here, as you can and actually we were stating that this relation F is equal to minus X dot. So like the restoring force, as we are familiar, the restoring force for the spring is equal to F is equal to minus Kx, where minus sign actually shows that the direction of this force is towards the equilibrium, means towards this point O reference. So the negative sign actually shows that, because this is the simple harmonic motion, because x is positive downwards, but the direction of the restoring force, as we can see here, this is the damping force and this is the restoring force due to spring constant. So both are actually restoring this mass towards the equilibrium position. So this is very important about this concept. So the magnitude for the damping force we have already actually learned the definition in the first chapter, that it is actually the damping force is proportional to the damper velocity, means the velocity with which this piston and cylinder system will be moving relative to each other, and depending upon the viscosity of the fluid viscous fluid used, the damping will increase or decreased. So that means that the damping force is directly proportional to the damping velocity and is directed towards the equilibrium position. So this is the statement, oral statement for this equation, that the damping force, which actually the author has shown using simply capital letter F, that it is directly proportional to the damping velocity x dot and is directed towards the equilibrium position O, or reference position. So small letter c is the damping constant. So this is the damping force, and the spring force or restoring force or elastic force, we are already familiar, that is equal to F is equal to minus kx. So here if we see its free body diagram, means the resultant forces, and as we can observe here that this is the restoring force of the spring and this is the restoring force due to damper, and as x is directed downward positive, if we apply the Newton's second law, so we can observe here that the Newton's second law simply states that the summation of F is equal to ma. So here all the external forces are negative because they are in the opposite direction of the assumed positive orientation of the displacement is directed downward positive and the forces are opposite to this direction. So that is the reason, because the summation of forces, and the inertia force is directed downwards because the mass is as a result of these restoring forces moving downwards. Remember, because this is actually the initial free oscillation, remember this is the free oscillation but damped oscillations. So we had actually performed the initial oscillation, and after the first or second cycle, when it passes the equilibrium and it is moving downward, so this is the state here. This is the state that the restoring forces are opposite to the direction of the response. So this is the equation as applied using Newton's second law, and now we will be simply manipulating it, and this is the standard equation mx this is the required governing equation, mx double dot plus cx dot plus kx is equal to 0. And here the very important thing is that this 0 actually represents the external excitation. Remember, what is the importance of this 0? The question is, what is the importance of this 0? While the equation has been written in this form, if in equation 2.59, this actually 0 on the right hand side actually shows the initial excitation, which is 0, means free excitation or free oscillations. If here were some functions of force or some other external force, so that were not the free oscillation. So mx double dot plus cx dot plus kx is the free oscillation, because c, k and m are system inherent parameters. Without any of these parameters disappearing, the system cannot retain its structure or shape. So mx double dot plus cx dot plus kx, and remember when equation written in this form, this is the non-standard form. This is the non-standard form, and this is the second order linear differential equation, second order linear differential homogeneous equation, second order linear homogeneous differential equation. And if we want the standard form, to write it in the standard form, what we will be dividing? We will be dividing this non-standard equation with the highest order derivative term coefficient. This is the highest order term coefficient m, so we will be dividing this equation throughout with m to obtain the standard form. Means in the standard equation the highest the coefficient of the highest order derivative is always 1. So to obtain 1 we can simply divide with the coefficient of the highest order term coefficient. So here the highest order term coefficient is small letter m, means the inertia, so we will be dividing this equation throughout by m to obtain the standard form. So the standard form you can write it yourself, that will be equal to x double dot plus c by m into x dot plus k by m into x is equal to 0. So that will be the standard form, which actually the author has not mentioned here, but you can check the literature from internet or some standard book. So as this is the governing equation, and as we have already observed in the start of this chapter that there are other methods to derive the same equation, namely law of conservation of energy, D'Alembert principle, and principles of virtual displacement or virtual work. So all those methods can be equally applied, but the author has not use those methods to derive these equations. So it is actually the duty and the responsibility of the student that they will themselves be applying those methods upon this equation 2.59. And in the exam they might be required, they can be asked, they might be required to derive the same equation using law of conservation of energy technique, using D'Alembert's principle. At least these two methods are necessary for the student because we have learned them previously. One is the law of conservation of energy technique and the other is the D'Alembert principle. So these two methods are the responsibility for the student, that they will be exercising them themselves. So if they have any problem they might ask me. So next comes the solution for this equation. This is the governing solution. So as we are familiar that the solution for a second order linear homogeneous differential equation, when it has the undamped oscillations, that was of the form xt is equal to c e s t, where c is arbitrary constant and this is the exponential function. So the same solution that we had actually supposed or assumed for the free undamped oscillations, the same solution has been assumed here for the damped oscillations, as the solution was assumed in the start of the chapter. So the equation 2.60 is actually the assumed solution for the response for this governing or modeling equation. So what we will be doing, that we will simply be doing its first and second derivative. Here we will be actually here x double dot or x dot or x is actually xt as a function of time, because this is the dynamic deflection. Remember, xt is not the static deflection, this is the dynamics deflection. So we will be taking its derivative, and as we have done in the start of this chapter, so when we will be taking its first derivative, so that will be x dot t will be equal to sc est, and when we will be taking its second derivative, so that will be x double dot t is equal to s square cest. So then we will be inputting these values of x double dot, x dot and x into this equation 2.59, and when we will be commoning, we will take common, cest will be taken as common. So these steps are here actually missed or omitted, and this is the responsibility for the student, that they will be taking a register and they will solve this equation in detail. Remember, they will be So we will be taking common CEST, and in the parenthesis there will be ms square plus cs plus k, and the next step will be that the equation will have become the product of two terms, means one term will be CEST and the other term will be ms square plus cs plus k is equal to 0. And now either of the two terms can be 0. Mathematically either CEST can be 0 or ms square plus cs plus k can be equal to 0, or both can be 0. But we are familiar that CEST can never be equal to 0, because we will again be explaining this fact that why CEST cannot be equal to 0, because if C is equal to 0 means there is no oscillation, because C is actually the amplitude of the oscillation. So if the system is oscillating, there can't be any case where the its random oscillation is actually 0. So C cannot be 0, and EST for any values is never equal to 0, because either s is equal to 0 or t is equal to 0, e power 0, this will be equal to 1. So for any value EST cannot be equal to 0. So we will be actually commenting in detail the reason why CEST cannot be equal to 0. So that will actually be resulting that ms square plus cs plus k is equal to 0. And again remember that this is called the characteristic equation for the corresponding governing equation 2.59. This is the corresponding governing equation, and this is its characteristic equation or frequency equation. We we can also say it to be the frequency or characteristic equation, because this equation will be directly giving the frequency, as we will be observing later on. So this is as we can observe here that this equation is quadratic in S, ms square plus cs plus k. So here we can observe that the using the quadratic formula is two roots will be s1 to 2, means two roots will be minus c plus minus this. So dividing it by 2m, here minus c by 2m plus minus. So equation 2.66 will be resulting. And here we can write here the, because it has two roots, so the initial solution assumed will be actually giving due to the roots two independent solutions. So x1t will be equal to c1 e s1t and x2t will be equal to c2 e s2t. And remember again that c1 and c2 here are again arbitrary new constant, because these constants have been introduced here due to these two roots which have been resulted from the solution of the characteristic equation, which was actually quadratic in S. So S has two roots, two values, so that actually gave us two independent solution. And when we have obtained these two independent solutions, we are familiar that for a linear or homogeneous system, we are familiar using the law of superposition or principle of linearity or linearity principle. We are familiar that the independent solutions for a homogeneous second order linear differential equation, the individual solutions can be summed up linearly to give the solution for the original equation itself. The linearity principle or the superposition principle is that the independent solutions can be simply added up, and they will also be the solution for the original equation. Means the independent solutions also satisfy the original equation, uh, the original governing equation, and if we simply add them like plus minus, so they will again be satisfying that equation. So this is actually the linearity or superposition principle, that the independent solution can be simply added up. So their simple addition without any other mathematical operation, that will also be satisfying the original governing equation mx double dot plus cx dot plus kx is equal to 0. So using the linearity principle, the uh, solution obtained at the initial level is actually c1e, and this equation 2.64, as you can observe it here. And now here the important thing is that this equation is actually a general equation. Equation 2.64 is the general equation, because here now we will this equation, as we can observe here, the exponent is very much complex and lengthy. So our next task will be introducing two terms, critical damping constant and damping ratio, to simplify this exponent of exponential value, exponential term. So here it says introduces two new terms, which is called, one is called critical damping constant and other is called the damping ratio. And as we can observe here, that the critical damping constant, it states that it is actually shown by or represented by small letter c and its subscript c. Remember, this is c mean critical damping constant. We will be reading it critical damping constant, and how we will be writing it? Clearly, small letter c and its again subscript c is defined as the value of the damping constant c, for which the radical in equation 2.62 becomes 0. So what is the definition of the critical damping constant? First of all, that it is actually that value of the damping constant for which actually that makes the radical sign under the equation, this is equation 2.62. It says here, because this part is actually specifies the nature of the roots. So for the critical damping constant, if the whole term under this radical sign or square root sign, radical sign means square root sign, is equal to 0, then we can say the value of c will be equal to critical damping constant. Remember, so this is actually the definition of the critical damping constant, that actually that value of the damping constant which makes the term under the radical sign equal to 0. So this is the simple definition. So here, as we can observe, we have replaced c by c subscript c, critical damping constant. So here the value of critical damping constant that comes out to be cc is equal to 2m and square root k by m, as you can observe it here, that and here as we can observe here, that this will be equal to 2 square root km, mean the product means critical damping constant will be equal to double of the square root of stiffness and its linear inertia. So we will be remembering this equation, and the other equation is that we can also write 2m and square root k by m is equal to omega m. So this equation can be written in two forms. This equation can be written in two forms. One is 2 square root km and other form is 2m omega m. And remember, students are required for the solution problem, for the solution of the problem point of view, they must remember these two terms, these two alternative values or terms, alternative forms, that One is 2 square root km and other is 2 m omega n. Means we can say the critical damping constant is actually the double or 2 times the product of the stiffness and its linear inertia, and for a linear system, remember. And or the other form is, it is 2 times the product of the linear inertia and its circular frequency omega n. Its value is its units are radian per second, 2 m omega n. So equation 2.65 has been clarified. After that, the author introduces the next new term, that is actually that says for any damped system the damping ratio, uh, this symbol zeta, we can say it, is defined as the ratio of the damping constant to the critical damping constant. So this value we can state it to be zeta, or damping constant we can simply read it, that is equal to C by Cc. Means the damping factor, this is called the damping ratio or damping factor. Remember, damping ratio or damping factor, because factor in this way that the value can be greater than 1, and ratio in this way that the value might be less than 1. So this is actually the ratio of the actual or real damping constant to the critical damping constant, where critical damping constant will be calculated always using equation 2.65. so this is the design equation, that if we are designing some system and we want to know the value of the critical damping constant, so we have the formula that we will simply be multiplying its stiffness, which will be calculated experimentally, and its linear mass, and take its square root and multiply it by 2. So this will give you the critical damping constant, or other is that we can note experimentally its linear frequency and multiply it by inertia and multiply it by 2. So in this way, so that will be calculated experimentally like this, and the this damping constant C will be actually consulted from the charts of fluids, of viscous fluids from the literature. So this will actually be giving us the damping factor or damping ratio equation 2.66. and here we can observe that using these two values, the radical sign term can be actually modified as that. Here it says that using equation 2.66 and equation 2.65, these two terms means the critical damping constant and damping ratio, we can write the radical sign, means C by 2m is equal to, how we can manipulate it, C by 2m, we will simply be multiplying and dividing it by Cc, critical damping constant, and as we can observe here that C by Cc is equal to damping factor by the definition of equation 2.66, and C by 2m here, as we can observe here, C by 2m will be equal to omega n. So C by 2m is equal to damping factor into omega n, equation 2.67. This is actually simply manipulating the terms under the radical sign. So here we can observe that the roots s1 s2, these roots, remember again equation 2.62 has been modified. So this equation, as we can observe, we will be putting here the values of C by 2m here, minus damping factor into omega n, and here again minus damping factor into omega n extra here, and K by m, as we are familiar, this is omega n, square root, the square root of natural or circular frequency of omega n. So here we can observe when we will be taking omega n as common, then here will be s1 s2 roots, so will be minus damping factor plus minus square root damping factor square minus 1 into omega n. Remember, omega n is actually the outside these parentheses, remember. So that is the taken common here, as we can observe that equation 2.68, and now we will be inputting this equation 2.68 into same equation 2.62, or we can say equation 2.64. so when put in this equation 2.64 will be modified into equation 2.69 here. So here, as we can observe here, that C1e, and this is the final equation for a general damped oscillation, free oscillation. So again, remember 2.69 or equation 2.64 are identical with each other. This equation is actually in terms of damping factor and natural frequency or circular frequency, in terms of damping factor and circular frequency, and the equation 2.64 was actually in terms of original parameters like damping constant or its linear inertia, etc. So actually these equations are alternatively can be used wherever. So this is the much simplified equation here. So this is equation 2.69 is the general equation. Here it says that the nature of the roots s1, s2, and hence the behavior of the solution of equation 2.69 depends upon the magnitude of damping. It can be seen that the case damping factor is equal to 0 leads to undamped vibration discussed in section 2.2. Here it says that if in this equation 2.69 we simply put the damping factor or damping ratio to be 0, so we simply obtain the equation of undamped oscillations as we had previously obtained in the first part of this chapter. So the other case, when it says hence we assume that damping factor is not equal to 0 for the damped case. So and consider the following three cases. So when the damping factor or damping ratio is not equal to 0, mean there is some type of damping, viscous damping. So it will have three cases. The three cases are such that case 1 is underdamped system. This will be called underdamped system. So what will be the statement for this? That the damping factor or damping ratio will be less than 1, or alternatively C will be less than C. C means the given critical constant or real damping constant for the fluid used will be less than the critical damping constant, or C by 2m will be less than square root of K by m. So these are the actually alternatively can be written. So we can state them differently. For this condition, damping factor square is negative and the roots s1, s2 can be expressed. So here important thing is that, as we can observe, if the damping factor in this equation 2.69 we can observe here at this stage, if here because it says that damping factor square minus 1, so if damping factor is actually less than 1, so its square will be less than 1. So when 1 will be subtracted from a value which is less than 1, so under the radical sign will be giving the negative. So that means the roots will be imaginary here, as we can observe here. So we will be writing it 1 minus damping factor square, and here square root minus 1 will be transformed into iota simply. So the radical sign, because in the underdamped case the damping factor is less than 1, because this is less than 1, for example you can say 0.1, 0.2, 0.3 or 0.9 whatsoever. So here the the roots s1 and s2, the roots s1 and s2 here in they will be actually transformed. Equation 2.68 will be transformed of the roots will be equal to minus damping factor plus minus, and here 1 minus damping factor square, and here will be iota into 1 minus damping factor square root into omega n simply. So here you can observe the roots will be transformed like this, and the equation will be like this. So this is the equation for the underdamped system, as we can observe here. Now as we had transformed or modified the equation in the first part of this chapter for the undamped oscillation, we will be modifying or manipulating it. So what the author has done, actually here we can observe here that we have written every term in the as the product of two terms. How? That this is C1, and here as we can observe that the power of E is minus damping factor and plus iota square root 1 minus damping factor square into omega n by omega n into t, and here we can write it as the we can observe that the exponent is actually are added up here, so we can write it here like this: e power minus damping factor dot e power iota square root 1 minus damping factor square into omega n. So we can actually write it here, as we can observe here, that from this equation e power minus damping factor into omega nt, this omega nt will be multiplied inside here, and here will be can be written as the product of two terms, so like this. So here we can observe that because this e power minus damping factor into omega nt is actually common in this equation, this first part is actually common for both the solutions, so that will be actually taken as common and will be brought outside the parenthesis, and inside the parenthesis there will be C1 and this value. So as it is very laborious for you to write this equation, so I have solved it here in a different way, as I can show you here that sorry so I have solved it here the case 1 with details. So I have assumed here let 1 minus damping factor square root into omega n as to be omega subscript t. We will be later on observing that this value other than iota square root damping factor square root of 1 minus damping factor square into omega n, because actually 1 minus damping factor square root is actually a dimensionless number, so this will be multiplied by omega n, means omega n is actually the natural frequency that will be multiplied by this square root value, which is actually you can say less than 1. So this is actually called the damped frequency. So damped frequency is always equal to the product of square root of 1 minus damping factor square into omega n. So we can at this stage we can also observe here that 1 minus damping factor square and its square root, this will always be less than 1. So that means omega n, because this is the product of two terms omega n and square root of 1 minus damping factor square. And if this term is less than 1, if because if this you can say if it were equal to 1, then omega d would be equal to omega n. But if this is less than 1, if this is less than 1, that means omega n is greater than omega d. So that means the natural frequency is greater than the damped frequency. So we can also state it like this, that for example, for 1 second, if omega n natural system undamped system has made 5 oscillation, for example 5 oscillations, so the damped oscillation will be less than 5 oscillations, means there might be 4 oscillations, 4.5, that means they will always be less than 1. So in a similar manner, as we observe that the time period or period of oscillation is always the reciprocal of omega d. So we can observe here the period of damped oscillation will be greater than the period of natural oscillations. So the time period of oscillation of damped oscillation will be greater than the time period of natural oscillation, but the frequency of natural oscillations will be greater than the frequency of damped oscillation. So this equation is actually stating this. So for the simplification purpose, actually the author will be later on using this formula, but I have used it here so that you are easier to write it. So this equation has been written in this form here. This equation has been actually started here like this, that e power minus omega nt damping factor into omega nt, and here c1 e iota omega dt and c2. Remember, this is the subscript omega subscript d, like this is not the product, this is actually omega, like this omega subscript n, so this is omega subscript d. So c1 e iota omega dt plus c2 minus iota omega dt. So this equation has been written in a more easier or more compact form using damped frequency. So here, as we can observe here, using the Euler identity or Euler formula, we are familiar that omega dt is actually the damped angular displacement. Omega d subscript is the damped angular displacement. So here we can observe here that the Euler formula we are familiar, that c we can write it here, c1 into e iota omega dt, we can write it cos omega dt plus iota sin omega dt, and similarly here c2, and here because it is minus iota theta etc, so cos omega dt minus iota sin omega dt, like this. And after that we will be actually commoning cos omega d terms and sin omega dt terms, and here we can say that this will be equal to c1 plus c2 cos omega dt and plus iota into c1 minus c2 into sin omega dt. And here we can introduce two new terms, as we had done in the first portion of this chapter in the undamped oscillation, that let c1 plus c2 is equal to c1 dash. In the start of the chapter, here were a1 plus a2, and here were a dash etc. So here the author has used a different arbitrary constant. So iota c1 minus c2, iota c1 minus c2, this has been transformed into another damping arbitrary constant. Remember, these are capital letters. C1 plus c2 is equal to c1 dash. These are capital letters because these are arbitrary constants. So always be careful that you must distinguish them while writing from the damping constant, so that is always written as the small case, and these are in capital case. So here, as we can observe here, that E minus damping factor into omega nt, and here it will become C1 dash cos omega dt plus C2 dash sin omega dt. So you have actually approached up to this fourth line here. So E minus damping factor omega nt, and here C1 cos omega dt and C2 dash sin omega dt. After that, the important thing is that here, as we can observe it here, that it has written in the compact form like the equation 2.21, as we had observed in the means the sine form or cosine form are in the compact form, because sine and cosine are actually the complementary function, and they can be actually compacted into compact form. So here this form is actually the cosine form, and this is the sine form, and both of them can be equally or alternatively can be used depending upon the user feasibility. So here, as we can observe here, that so how those equation will be derived here. Equation 2.70 both parts. So if we want to transform the previous equation in the cosine form, so we will be assuming here like this, that let C1 dash is equal to some common displacement, means this is the this is the component for a for an amplitude. So here this constant, because these constants are actually introduced due to the phase shift, so C1 dash is equal to capital X cos phi. So in the form of phase shift, because in the form of phase shift, that can be actually expressed as C1 dash is equal to X cos phi. We have done the similar assumption in the start of the in the first part of this chapter. So C1 dash is equal to X cos phi, and C2 dash is equal to X sin phi. Here you are actually remember, but I can show you it here. Here, sorry, here, as you can observe it here, that we had used this equation 2.19, that the same methodology is used for the damped oscillation in the damped case here, as we had assumed. So now go here, and as you can observe it here, that this C1 dash is equal to X cos phi and C2 dash is equal to X sin phi, etc. Or alternatively, if we want to write in the sine form, we can assume these constants to be X dot sin phi naught, C2 dash is equal to X naught cos phi naught, etc. So in this form we can write them. So here we can observe, when we will putting X cos phi cos omega dt plus X sin phi sin omega dt, so that you can write it here, that cos alpha plus cos beta formula, that X cos omega dt minus phi, because here the plus sign, so it must be minus sign here. So after putting the value of omega d, so this is equal to this value. So this is the equation in the cosine form of 2.70 equation. and in the sine form if we want to write, so we will be inputting the other value x naught sine phi naught, the value of c1 dash, and the value of c2 dash x naught cos phi naught, etc. So in the form of sine alpha plus beta, the formula will be equal to sine omega dt plus phi naught, and again inputting the value of omega dt. So this is the formula derivation for equation 2.74. And here as we can observe that x or x naught, so student might question that why is used here x naught or capital X. So just to distinguish the sine and cosine terms, and there is no other reason. So here as we can observe here, where c1 dash c2 dash x phi and x naught phi naught are arbitrary constant to be determined from the initial boundary conditions. So the initial conditions we are familiar. This thing has been explained many times in the start of this chapter while we were deriving these equations for the undamped oscillations. So student can consult that lecture from previous dates. So here as we can observe that the initial boundary condition are used, or at time 0 the initial displacement is x naught, and at time 0 the initial velocity of the mass is actually x dot naught. So here as we can observe that c1 dash can simply be obtained from this equation, because this was the actual equation in terms of c1 dash and c2 dash. So here xt, we will be putting x0 means x naught, so that will be equal to, when we will be putting here e power minus damping factor omega nt, so this will be the e power 0, so this is equal to 1. And here when we will be inputting, so here we will observe cos 0, because here t that will be multiplied by 0, cos 0 that will be equal to 1, and here because this is the sine 0 is equal to 0, so x naught will be simply equal to c1 dash. So the same has been done here, c1 dash will be equal to x naught. So and the other constant is c2 dash, that will be equal to, so how this constant will be obtained. So I have solved it here for your facility. As you can observe it here, initial conditions have been used it here. So equation 1 give x naught directly c1 dash, and after that we will be differentiating xt to find x dot t. Remember, we will actually be differentiating, taking derivative of this equation x dot t of this equation. And as we can observe, this is the every term is actually the product of two functions. One function is e power damping factor omega nt, which is the actually common function, so we can simply be multiplying it inside. So here will be one function this, because this is the function of time and this is also the function of time. As we can observe it here, this is also the function of time and this is also the function of time. So the product of two functions formula will be used. The derivative of the product of two functions formula will be used, remember, in this equation. So when this formula will be used here, I have used it here omega d just for simplification purpose in that equation. So as we can observe here, this is the first function, for example, and we will be taking the derivative of the second function completely, so that as we can observe it here, that cos derivative will be equal to minus sine omega dt, because this value is actually omega dt, as I have already used it, and this will be equal to sine omega dt, so its derivative will be cos omega dt c2 dash. And after that and as we can observe it here, that when we will be taking the derivative, the omega dt derivative will again be taken, that will be equal to multiplied here into omega d, and here omega d. So I have simply taken it out. So this omega d is actually being multiplied here with this term and with this term. So you can simply take its derivative. If you have any confusion, you can solve it yourself using register and pages. And after that, the second function, this is the second function, and we will take its derivative, and the first function will be written as it is. So after that, we will be inputting the x dot t time 0. So when this will be used, as we can observe it here in the next slide, that when time 0 will be input, so we will be observing that this will be equal to omega dc2 dash here, as we can observe it here. When we will be inputting time 0 here, as we can observe here, this will be become equal to 1, and here this term will be equal to 0, and this term cos omega dt will become equal to 1. So c2 dash will be multiplied by omega d. C2 dash will be multiplied by omega d. So the same has been done here, as we can observe, omega d c2 dash minus the other term will be equal to, when we will multiplying it, so this will be equal to 1. So minus damping factor into omega n, minus damping factor into omega n, and here will be c1 dash. So c1 dash minus c1 dash damping factor into omega n, here this term will be obtained, as you can observe it here, c1 dash minus c1 dash damping factor into omega n. So from here we will be, the value of c1 dash is equal to x naught. I have used that value input, and here c2 dash you can obtain it here, that c2 dash will be equal to omega d c2 dash will be equal to this, and c2 dash will be equal to x naught plus damping factor x naught omega n divided by omega d. So the input the value of damped frequency here, so you actually obtain c2 dash is equal to x naught is equal to 0, x naught x dot naught plus damping factor x naught omega n divided by 2, and you can compare it with this equation c2 dash, as we can observe it. So equation 2.71 has been obtained. So these were difficult for the students to obtain, so I have placed them on the track. So after that we will be inputting these values, and this is actually the final result for the damped oscillation, for the underdamped oscillation. Equation 2.72 is the final result of the response for the underdamped oscillation in terms of boundary conditions have been calculated. And after that we are familiar that these constant x and phi, or x naught and phi naught, can be simply obtained. We are familiar that as we can observe here, as I have already told it here, we have done it in the start of the chapter, that as we had made these assumption. So here c1 dash c2 dash, so if we want to find x, so what we will be doing, we will be taking its squares and we will be summing them up, c1 dash square and c2 dash square. So when they will be added up, so cos x square cos square phi and x square sin square phi, so x square will be taken common out, so x cos square phi plus sin square phi will be equal to unity, because this is the identity. So that means capital X or x naught in this case, both will be equally actually satisfied using this. So this formula will be used, and we can simply put the values of c1 and c2, and equation 2.73 will be obtained. And remember, this simplification is the responsibility for the students, that they will be doing it themselves. This is their responsibility, because I have place them on the track, and after that simply we can obtain phi naught and phi. In a similar manner, I hope the student have understood that we will simply be dividing for the if we want to use phi, if we want to determine phi, so what we will be doing, we will be dividing equation c2 dash by c1 dash. So we will be dividing it, and x will be actually cancelled out, and sine phi by cos phi will be transformed turned into tan phi. As you can observe here, phi will be equal to c2 dash by c1. So here input the values of c2 dash, and we will obtain equation 2.73, 2.74 and 2.75 have been clearly derived without any confusion. So here the derivation for the underdamped oscillation has been completed in all aspects. After that, the author states the same fact which I have already explained, that the motion described by equation 2.72 is a damped harmonic of angular frequency of 1 minus damping factor square root into omega, but because of the factor E minus damping factor into omega n, the amplitude decreases exponentially with time, as shown in figure 2.22. So here in this statement, the important thing is that if you observe this equation 2.72, this is very important. As you can observe here, the author actually states that instead of using equation 2.72, you can simply use this original equation. So this equation, as we can observe here, that it says that c1 dash cos omega dt plus c2 dash sin omega dt. So actually, as we are familiar that this is actually the damped frequency, this is actually the damped frequency, and damped amplitude will be less than the natural amplitude, but its amplitude will remain constant throughout the series. Here if you can observe it here, I can just make you understand it here. For example, just simply, for example, assume that this is you can say vertical axis, and this is the horizontal axis. Actually, if for example I am using here, this is the damped oscillations like this here. Here it actually states that when we will be actually plotting this equation, so the only difference will be that if this term, for example, for a moment you suppose or assume that this term is vanished or this term is not there, you are only considering this the solution inside this parenthesis. So how its form will be here like this, because this will be the damped, but the this peak and this peak has the same elevation. Here again, for example, you can further add further cycles, means for example here we can just for visualization, these all these peaks will be at the same elevation. There will be this amplitude will not be decreased, remember, but again this is the damped oscillation, and for the case of if there were undamped oscillations, so that would be equal to like this, means their amplitude will be actually increased here like this. this will be the free oscillation. This is the cycle for free oscillations, and this is the cycle for the damped oscillations. So that the author actually states in that statement that the multiplication of this term is actually stating that here, as we can observe, the power of exponent is negative minus damping factor omega nt, because due to this negative, the author says that every next cycle amplitude is actually decreasing exponentially. Here, as you can observe here, because this amplitude and this amplitude is decreased exponentially. So this is actually this curve is actually controlling the peaks of the damped oscillation. So this is actually, as you can observe here, the author has used it here with the arrow symbol highlighted here, that xe minus damping factor omega nt. So actually the term xe minus damping factor omega nt is actually controlling the peaks of the damped oscillations, because if this term was disappeared, so this peak will be equal to at this elevation, and this peak will also be at this oscillation. So as I have told it here, that this peak and all peaks are at the same elevation but less than its corresponding natural oscillations. So that is actually the reason that has been described it here. So that means actually this term is actually controlling the amplitudes of the damped oscillations. So this thing has been stated here in this term. The motion described by as a damped oscillation, because of the factor E damping factor minus omega nt, the amplitude decreases exponentially with time, as you can see. So the quantity omega t is equal to damping factor 1 minus damping factor square root into omega n is called the frequency of damped vibration or damped frequency. So this formula is very, very important, that you will be remembering it, that if you are given the natural frequency and damping factor, you can simply calculate the damped frequency. So as I have already explained, that the damped frequency is less than the natural frequency, or natural frequency is greater than the damped frequency and the time period, or vice versa. So in this way under damped case has been completed. So again here you can read it here. It can be seen that the frequency of damped vibration omega d is always less than the undamped natural frequency omega n, and the time period will be vice versa, because if you can manipulate this statement as to be, it can be seen that the time period of damped vibration tau subscript d, we can tau time period, so tau subscript d is always greater than the undamped time period tau n, tau subscript n. So the decrease in the frequency of the damped vibration with increasing amount of damping given by equation 2.76 is shown graphically in figure 2.3. The underdamped case is very important in the study of the mechanical vibration, and it is as it is the only case that leads to an oscillatory motion, because it actually gives you cyclic motion or periodic motion like this, as you can observe here. And I have explained it to you that the equation was actually the product of two terms. One was the exponential and other was inside the parenthesis. So this bold, remember, I am again explaining this thing that this graph, this bold graph, which is actually the solution or plot of equation 2.72 complete. When we will be completely plotting this equation, we will be obtaining that solid plot. But if we only plot, for example, this term without this exponential product, for example, you assume that the terms inside the parenthesis are not appearing here, they are disappeared, they are not counted, and only this function is plot, e exponential function is plot e power minus omega nt, then we will be obtaining this dashed this dashed curve is actually the exponential plot, which is actually controlling the peaks of the oscillations. And as I have already told, if this term is actually disappeared, then you will be obtaining, there will be no decrement of amplitude of damped oscillations, as I have told it here, that these peaks, all peaks will be at the same elevation. But if we are plotting the complete equation 2.72, we will be obtaining actually this solid plot. And remember, when we have used the complete equation, practically these dashed curve will not be actually shown. The actual plot is this. These are actually just for explanation purpose, the author has created them for your clarification only. So actually it has taken time, but that was very important. So next comes the second case. And second case is critically damped constant, critically damped system. So for the critically damped system, the situation is that the damping factor must be equal to unity, or the C must be equal to C subscript C, or means the given damping constant is equal to critical damping constant, or C by 2m is equal to square root k by m. In this case, the two roots S1 and S2 in equation 2.68 are equal. We are familiar that if the discriminant part is 0, both the roots of the quadratic equation are always equal. So S1 and S2 is equal to minus C by 2m, simply means in that case, and as we are familiar that C is equal to 2m omega n, so 2m by 2m will be cancelled out, and here it will remain S1 and S2 will be equal to minus omega n. So as we can observe it here, that for the critically damped system, both roots are equal to the negative of the natural frequency or circular frequency. For the case of critically damped system, critically damped system, both roots are actually the negative of the natural frequency or circular frequency, equation 2.77. so when we will be inputting these two roots, so as the damping factor is 1, so e power damping factor is 1, so minus omega nt it will become. And here important thing is that, again, like this equation, I can explain it here. Equation 2.69 was the general equation. Remember, equation 2.69 was the general equation. So here, as we can observe it here, that the damping factor is 1. So the here the roots will be equal to c1 e minus omega nt, and here again will be equal to c2 e minus omega nt, because damping factor square minus 1 square root will be equal to 0. So that means, because both solutions are identical, so you can say we can simply multiply one solution by 2, because here in this case, using the linearity principle, both solutions are simply added at s1 s2. So there is no radical sign and both roots are equal, so we can simply say that they can simply be multiplied by the 2. But actually this is not the case. When the roots are equal, to make both the solutions distinct, it is actually the convention of the calculus that we will be multiplying or dividing the other solution with the independent variable, which has been done here. As you can observe here, that the second root c2 has been multiplied by simply t, as you can observe here, that because actually c1 was the solution was c1 e minus omega nt, and the other solution was c2 into e minus omega nt. So to make this solution distinct from this solution x1t, we have multiplied it with the independent variable time. So we could also divide it, but instead of dividing, we actually usually multiply it. And if, for example, I can say, if there were some third term, for example c3 e or minus omega t, so we could multiply it by that term by t square. And in a similar manner, for example, if we had the four solution, for example 4 roots, so the fourth solution would be multiplied by with t cube. So that doesn't affect the original solution. So this solution has been obtained. And again here the question will be to determining these constants c1 c2 for the critically damped case. So the methodology is same, that we will be at time 0 x naught will be obtained. So how that will be obtained? If we are putting x at time 0, so that we can observe it here, that this will become 1, and here this will become, so x naught will be equal to c1, as we can observe here on the next page. C1 will be equal to x naught, and after that it's we will be taking its first derivative to obtain x dot t. Remember, without putting 0, first of all we will taking its derivative. So when we will be taking its derivative, that is quite simple. Here will be equal to, you can simply take a derivative yourself, because that was quite easier, so I have not solved it. So here will be equal to minus omega n into c1, and here will be equal to here t multiplied by e minus omega nt. This is the product of two functions, so you can apply the product of two functions formula for the derivative. So when you will be applying the derivative formula, so this is the left over to the students. This is the responsibility for the student or assignment, that they will be solving equation 2.79. they will be verifying it, that c2 comes out to be x dot plus omega n x naught, because I have already told for the underdamped case that was much more complex. So for this simpler case, student can solve it themselves. So, and the solution, when we will be inputting those values, so this solution will be equal to 2.80. So here, as we can observe it here, that it can be seen that the motion represented by equation 2.80 is aperiodic. Aperiodic means non-periodic, means it has no oscillations, mean only one cycle will be there, and that will be simply vanished. So because why is aperiodic? Because there is no sine or cosine functions, as we can observe it here. There is no sine or cosine function, so this is a aperiodic motion. So as we since it is actually explained that e power minus omega and t tends to 0 as t tends to infinity, because this is actually controlling the period of the amplitude. This is actually controlling the period of or the amplitude of oscillation. So it says that as t tends to 0, because as we can observe it here, the power is minus, so this will become in the denominator, and as t will become infinity, as we can observe, so something this factor and divided by this term, so something divided by infinity is equal to 0. So that means, that states it here, so means the amplitude xt will become 0. So that means the motion will be eventually diminished to 0. That it actually says that xt will be equal to 0 as indicated in figure 2.24. so you can say it here, this is figure 2.24, and this is the critically damped case for this, as you can observe it here. So this amplitude will be fastly decreasing here, and here this is actually has transformed into 0 as the time is actually tends to infinity. So this case has been completed. After that, the third case that is very important and a bit work requires rough work, that is overdamped case, overdamped system. And for the overdamped system, as we can observe here, the damping factor will be greater than 1, or c will be greater than c subscript c, or in this value, and as we can observe it here, the equation 2.68 shows that the roots s1 and s2 are real and distinct, because in the discriminant there will be no negative sign, so means both roots s1 s2 are real. Distinct means they are actually real numbers, and unequal. Remember, these roots are real unequal, and here it says s1 minus damping factor plus damping factor square root into omega n is less than 1, and both roots are actually less than 1, means both roots are less than 0. Both roots s1 and s2 are less than 0. Less than 0 means negative. Both roots are negative. Both roots are actually negative. How? Because here, as we can observe here, for example, if damping factor is because greater than 1, for example, I can assume the damping factor to be, for example, 1.3. For example, you can assume the damping factor to be 1.3. So here minus 1.3 plus, as we can observe here, that we will be taking the square of 1.3, and from that square we will be actually subtracting 1. So when we will be taking its square root, you can calculate it yourself. I can show you it here, that 1.3 square minus 1 will be equal to 0.69, and when we will take its square root, so this will be equal to minus 0.83. So damping factor means that will be equal to minus 1.3 plus 0.83. So when we will be subtracted 1.3, so the result will be equal to minus 0.469 minus 0.469. So as this is also the negative root, the value is minus 0.469. And for this case again both roots are actually negatively summed up, so this is clearly also this will always be negative. So both roots whatsoever is the value is selected for the damping factor, and the value must be greater than 1. Remember, the value must be greater than 1, so both roots will be negative. And again here it says very here that s2 is this double less than sign actually is read out very less, means with s2 means the second root, this s2 root will be very less than, that means this root s2 will be more negative than the root s1. So s1 root will be less negative and s2 root will be more negative. So this is read out very less, s2 root is very less than s1 because as we can observe it here that 1.3, because here the second root will be equal to minus 1.769. so as compared to the first root that was actually minus 0.469, the second root s2 is equal to minus 1.769 when the damping factor is assumed to be 1.3. so for this specific I have taken a random value for the damping factor. So you can, so the equation 2.69 will be transformed like this, and as we can observe here that equation 2.81 and equation 2.68 sorry, equation 2.69 as you can say, this equation is as it is in this form is actually you can say this equation as derived is for the overdamped case, because this equation has not been changed. You can compare equation 2.69 and equation 2.80 sorry, equation 2.81. you can compare this equation 2.81 is same as the equation 2.69, there is no difference. So for this again we will be using the boundary conditions for the initial condition, and we will be obtaining these constants. And for your facility, because these constants were laboring, so I have solved one constant for you here. For the overdamped case, here sorry case 3 overdamped, here as we can observe it here I have used it here the just to save writing efforts, just to save writing efforts I have used these exponent as s1 s2 because these are constants, so I have used them here just to save writing efforts. So c1e s1t and this is c2e s2t here, so just to save efforts. So here when we will be inputting time 0 into we will be obtaining simply this equation that time 0, so c1 plus c2 x naught will be equal to c1 plus c2. So this is equation number 1, and after that we will be taking its time derivative x dot t. So when we will be taking its derivative x dot t, so this will become simply s1 c1 e s1 t and s2 c2 s2 e s2 t. So after that when we will be inputting time 0 in this equation, here, just a minute. Here like this is here, as we can observe it here. So when we will be putting time 0, so this will actually become, because e by s1t will be equal to 1, so s1c plus s2c, s2c2, and after that we will be using from equation 1 we are familiar that c1 is equal to x naught minus c2. So put this equation, put in equation number 2, so x dot t s1 into x naught minus c2, and here like this you can observe it here. Remember here must be the plus sign which has been mistakenly written here. So s1 x naught minus s1 c2 plus s2 c2, so here must be plus which has been mistakenly written. So here we will be obtaining s1 minus s2 into c2, so c2 here it will be equal to s1 x naught minus s1 into x naught minus x dot naught over s1 plus s2, and when we will be inputting the values of s1 and s2, the original roots, so here as we can observe it here, this solution, the values will be input here. So as we can observe here, minus damping factor omega n will be cancelled out, and this will be equal to like this, minus x naught omega n into, because here as you can observe that here actually omega n x naught is actually you can say negative sign is taken common from this term, so this negative has been multiplied with omega n x naught, so minus omega n x naught, and inside the parenthesis will be equal to damping factor minus square root damping factor square minus 1. So this equation has been transformed like this to match the equation written in the textbook here. So the value of C2, as you can observe here in the on the next page, I have actually derived the value for C2, so you can compare this equation with this equation. So for C1 use equation number 3 and put the value of C2 and solve it, do it yourself. Remember, do it yourself. So half portion I have done, and the remaining half you can do it yourself. And after that what you will be doing, that you will be inputting the values of C1 and C2 into equation 2.81, and this will you giving the equation for the overdamped system. So in this way, after that these two conclusions are three conclusions are shown here. So leave out the first conclusion. The second conclusion, it says, this is important for you to understand: a critically damped system will have the smallest damping required for a aperiodic motion. Again we can observe it here that equation 2.81, which is the equation for the overdamped system, this is also aperiodic motion because there is no sine or cosine function. This is also the aperiodic motion. This is also the aperiodic motion, non-periodic motion. And critically damped is also equation 2.80 is also aperiodic motion. Only equation 2.72 etc., that equation for the underdamped case was actually periodic motion. And here as we can observe in equation figure 2.24, it says that, as we can observe it here, this solid line is actually undamped case, means free oscillation compare, and this as you can observe it here, this dashed pattern, this is actually the under damped case, damped factor less than 1, omega d is smaller than the natural frequency. As we can observe here that this amplitude, the amplitude of natural oscillations are closer, means its frequency uh, is greater, and the wavelength is smaller. The wavelength for the natural oscillation is smaller as compared to the wavelength for the damped oscillations, because here, as you can observe, the wavelength for this under damped cases from this point to this point, but here from this point to this point. So the wavelength for the natural, or you can say undamped oscillations, is smaller as compared to the wavelength. So because the wavelength for the damped oscillation is greater, so the frequency is smaller, and the time period for the larger wavelength will certainly be greater. So the time period for the damped oscillation will be greater. So this is the reason. And this is the over damped case, as you can observe it here. So and this is the under damped case, and when compared all these four oscillations, means natural oscillations, under damped oscillations, critically damped oscillations, and over damped oscillation, we observe it here that only the critical damping curve is actually briskly, or before or first of all is actually its amplitude is becoming 0, means this the highest damping is actually obtained not in the case of over damped system, but in the case of critically damped system, because the over damped system, it is actually damped later. Here its amplitude is 0, is becoming far beyond the critically damped curve. This is the over damped curve. So in this means by the simple nomenclature, over damped actually depicts or represents that this must be the highest type of damping, the maximum damping, but this is not the case. The highest damping is actually obtained only in the case of critical damping constant, because it briskly or fastly dampens or lessens the amplitude of the vibration. So the same fact has actually been described here. Hence the mass returns to the positions of rest in the shortest possible time without overshooting. The property of critical damping is used in many practical applications. For example, the large guns have dashpots with critical damping value, so they return to the original position after recoil in the minimum time without vibrating. So here it states that the same critical damping constant system is used in the shooting guns. If the damping provided were more than the critical value, means for example over damped, as because that is greater than 1, some delay would be caused before the next firing. So because that is the very important process, so for that the critical damping system is used, not the over damped system, because the over damped system will be causing delay for before the next firing. And just this second clause is important for you, leave the third one, and after that our next topic will be logarithmic decrement, that we will be covering it in the next lecture. Thank you. Because about 2 hours time is going is there. So if you have any question, you can fairly comment and I will be answering. Thank you all. Regards. Assalamu alaikum.